Hello everyone, here I want to discuss 7.1, which is integration by parts. So in order to do that, let's first recall the product rule of derivatives. So if you take the derivative of a product of two functions, f of x and g of x, it's equal to f prime of x times g of x, plus the other way around, f of x times g prime of x. In other words, it's the derivative of one of them, leaving the other one constant, or not taking its derivative in other words, and then plus doing the other way around. In fact, this honestly generalizes if you have more than two functions in a product, but that's a little beyond what we want to discuss here. More formally, or I guess less formally, if you let u equal f of x and v equal g of x, then the kind of shorthand notation for the product rule is that uv prime, so its derivative, is u prime v plus uv prime, like that. And actually, if you consider this, and if you, let's say, I don't know, integrate both sides with respect to x, notice when you integrate the sum, there's an integral property that you can take the sum of the integrals. So the integral of the sum of the integrals, and this is all, of course, with respect to dx, which I'm not, or with respect to x, which I'm not writing. And here, if you take the integral of the derivative, they cancel out, so you just get uv equals, we can write u prime actually as du dx if we use Leibniz notation. But remember, since I'm writing a dx here, those dx's can cancel, and one can think of this as actually v times du, plus, similarly here, if we did have the so just to kind of show you real quick, if we did have the dx attached to it, then we can write v prime and similarly u prime over for this integral here as dv over dx in Leibniz notation. And notice what happens in that case is the dx's cancel. So we can actually write this as u dv. And speaking of which, if you actually solve for u dv in terms of everything else, that's just subtracting this integral of v du term to the other side, we end up with this formula here, which is known as the integration by parts formula, or IBP for short. So now we're going to actually use this formula to hopefully undo certain products. Now remember, this falls out from essentially reversing the product rule. So integration by parts is very often thought as the product rule for integrals, basically. So the opposite of product rule. Kind of like how u substitution is the opposite of chain rule, this is the opposite of the product rule. So if you ever have a product of two functions, especially if they're different types of functions, and notice here we have x times sine of x, so it's a polynomial times a trig function. Here we have x times e to the x, so it's a polynomial times an exponential function. Then we can try to apply integration by parts. Now the way I want to show this is I'm going to create a table where we have u and dv here. Now the idea is that eventually we're going to develop uv and then u du. So the idea is you have u and v like this and their derivatives below. But normally I write these ones first because from our formula, that's what we want this integral to be set up as, and then we can expand it out so that part of it is outside of the integral, but another part of it still needs to be integrated, hence the name by parts. So what do we want u to be and what do we want dv to be? Well, notice since this integral is the product of x and sine of x, these are kind of our choices. But to be quite honest, once u is selected, dv is everything else inside of the integral. And I'm just going to tell you that we're going to let u equal x, so that dv is everything else, which is sine of x, and yes, even the dx. And we'll kind of see something similar to what we saw in substitution rule or in u substitution. If u is equal to x, then du is the derivative of that times dx. In other words, it's just dx. This basically says if u is equal to x, then their derivatives are equal, which makes sense. And here we want to antiderive sine of x, find the antiderivative of sine of x to get from dv to v. And in doing that, that loses the dx kind of in reverse of this, is similar to this. Here we gain a dx when we find the derivative. Here when we take the antiderivative, we lose a dx. Now the antiderivative of sine, of course, is negative cosine of x. And now all we need to do is apply the by parts formula. So notice it says uv, so here's u times v, minus the integral of v times du. And here's v and du like this. Okay, good. So now this formula according to, or this integral anyways, according to this formula, is equal to, so I'm boxing this so it doesn't get in the way of the work, this is like background so to speak, uv, so it's a negative x cosine of x, minus the integral of v du, so it's negative cosine of x dx. Notice we can pull the negative on the outside, essentially canceling it out, because we have a double negative basically. And then finally the antiderivative of cosine is positive sign, so this is negative x cosine of x plus sine of x after taking the derivative, antiderivative, and then finally plus c since we're done with all integrals. Remember, once you're integral free, you write plus c. And there we go. In fact, that's really it. But notice the process here. The integral involved the product of two functions, but then applying the correct setup for integration by parts makes the new integral a lot easier to handle based on more, I guess, basic antiderivatives. And that's kind of the goal, to simplify this integral. Great. So now here, similarly, this is going to be our u and everything else is going to be dv. So let's see if we can have a similar setup. So u is x, that means du is dx, very, very similarly. And right here, dv is equal to everything else, which is, of course, x e to the x dx. Antiderivative e to the x is itself, so we get this. And then now finally applying the rule, or the formula for by parts, we get u times v minus the integral of v times du. So I very often like to set it up like this because we see this pattern like that. Some people do it the other way, but I like this because we see u and v and then the derivatives below. But that's just my way of explaining it and doing it, of course. Take it. So uv is going to be, so this integral is equal to x e to the x minus the integral of v du, so that's e to the x dx. And notice this integral is definitely easier to do than the original because this is just a basic antiderivative. So antiderivative e to the x is of course itself. We write plus c because we're integral free. And yeah, you can check if you want, but notice, since integration by parts is indeed the opposite of product rule, to check, expect to use product rule somewhere. In fact, we'll use it here, not for this one, and then here, but not for this one. In fact, really what these counterparts do, these non-product rule parts, is that when you take their derivative, it'll cancel out part of the product rule and basically leave only this part of the product rule. Which is kind of interesting. I'll leave that to you to check on your own. And now we're going to look at a few more examples. All right, so here we have a few examples, 4 examples. And you'll notice that the top 2 aren't actually products. Also, you'll notice we have now some definite integrals where we have limits. I'm just going to tell you, you can apply the limits to the very end. To be quite honest, if you want, you can evaluate what's already outside of the integral from the integration by parts formula one at a time. But honestly, it's best to just do it at the very end. So now, in regards to these two, they're not products. But believe it or not, by parts actually still applies. Now, it's not obvious by any means that that's the case, but you kind of really just know by practicing these things that that is really the only thing we can try that actually works. So, if we try integration by parts here, we need a u and we need dv. And we only really have one choice. Well, I guess we have 2 choices for u. Either u is 1, because technically this is 1 times ln of x, or it's ln of x. Now, u will be ln of x. If it was 1, then notice dv would be ln of x, and to find v, you would have to find the antiderivative ln of x. But if we knew the antiderivative ln of x, we wouldn't even be applying integration by parts. We'd just be done already. Okay. So that makes this choice obvious. But again, the only thing that's not obvious is how do you know to apply integration by parts. But we'll talk a little bit about a kind of way we can tell later on. Then du, of course, is the derivative of ln of x, which is 1 over x dx. dv has to be everything else, which is, of course, just dx. Its antiderivative is just x. And now if we apply the formula for integration by parts, which remember is uv minus the integral of v du. So it's going to be x ln of x minus the integral of v du is x times 1 over x dx, like that. And notice here these cancel, so we just get the integral of 1 dx. Antiderivative of 1 with respect to x is just x. So we get x ln of x minus x, and then write plus c finally, since we're integral free, and that's our answer. And remember, this is equal to that integral, this is equal to that, and this is happening in the background to help us proceed in the integration. And of course, you can check this. You'll have to use product rule, of course, here. And that's all I'm going to say as far as this one goes, but we'll talk a little bit more about that later on when we get to this example finally. And here, it's actually very similar because we don't have a product necessarily, it's just one function. Tangent inverse of x is one function. Remember, it's not tangent inverse times x, it's tangent inverse of x. Just like this is ln of x, not ln times x. Good. So now what? Now we're going to do the exact same thing really we did, and with the same logic. U has no choice really but to be tangent inverse. Otherwise, if it was dv, then we would already know its antiderivative, and we wouldn't need to continue. So what's du? Well, du is the derivative of tangent inverse, and if you don't recall, that's actually 1 over 1 plus x squared. So let me just scoot this over for a little bit more space. So I have 1 over 1 plus x squared, don't forget dx. dv then has no choice but to be just dx, so that v is equal to x. And now again, applying the integration by parts formula, and I'm realizing maybe we don't have enough space here, because unlike the previous examples we've seen, the integral that we're left over with the by parts formula in this case will be a little bit complicated. It's not too bad, but it's a little bit complicated. So uv is going to be, so remember this is background, so box it just so it doesn't get in the way. uv is x tangent inverse, good. Minus now this kind of complicated integral, which is 1 over x squared times x, so I'll just include the x in the numerator if that's okay. And I'll talk a little bit about how we're going to handle this. In fact, right now, I'm going to border this off so I can kind of continue this way, and then I'll erase later when we can continue to these two bottom examples here. Also notice we have the limits to take care of, but again, ignore the limits until the very end. Just don't forget about the limits. Otherwise, you have to evaluate these, and then it gets weird because you're kind of doing different things at different times. So for that reason, I think it's more consistent anyways, just to handle the evaluation at the very, very end. Now, here, what we're going to notice is that the denominator has a derivative that is a constant multiple of the numerator. In other words, we're going to use u substitution, and we're going to let u equal the denominator 1 plus x squared, so that du is equal to, well, 2x dx. And notice x dx is actually right there in plain sight. X dx in this integral is right here. So with that being said, we can solve for x dx here and get 1/2 du is equal to x dx. Remember, this is just a substitution, which is obviously from the previous section. Okay, so if we apply this here, then x dx is replaced with 1/2 du. The 1/2 we can pull out of the integral, so we have negative 1/2. Integral of 1 over u now, du. And this is good because the integral of ln of u, of course, ruined it. The integral of 1 over u, of course, is, now you can say it with me, ln of absolute value of u. So this is negative 1/2 ln of absolute value of u. And then this comes along for free each step of the way. That's a part of that. And now, of course, we know u is 1 plus x squared, so I can just replace it here. That's all right. After breaking through the integral, then we back substitute. And now we can write plus c, but we don't need to write plus c, of course, because there are limits. Now we will consider the limits, and we'll see what happens when we plug them in. There's really good news when you plug in the bottom limit 0. This will be 0, of course, because it's x times this, so it's going to be 0 times that. By the way, tangent inverse of 0 is still 0 anyway, so this is 0 regardless. Minus 1/2 ln of, when x is 0, the inside here is 1, ln of 1 is 0 also. So this we actually don't need to even worry about because it's just going to be a minus 0. So it doesn't really affect our answer. So then plugging in 1 is all we really need to do. So it's going to be 1 times tangent inverse of 1 minus 1/2 times ln of 2. And notice we don't need absolute values there because 2 is positive. Also, tangent inverse of 1 is pi over 4. So the answer here really is just pi over 4 times 1/2 ln of 2. So now I'm going to erase a lot of this work, in fact all of it, and just move this up just to remind us that was our answer, and then we'll continue with these bottom two examples. All right, so here, like I said, I erased and I wrote our answer we got. I also wrote a few different ways you can simplify it a little bit, and you can think about those if you like, but I'm boxing all of them because they're all as acceptable. They're just different simplifications, depending on how you're feeling, I guess. Here, we want to use by parts because we have a product, x to the third times ln of x. But we're, of course, brought up with the question we were brought up before. Which one's u? Because notice that's the only question. Once we know u, dv is everything else. So we want to find u, and then dv will be established. Now, I gave you the idea that the polynomial part will always be u. That's not the case. For sine of x, in fact, for any trig function, that's the case. When you have it multiplied to a trig function. Similarly, when you have it multiplied to an exponential, that's also the case, like we saw in the previous two examples before these two. But ln of x actually has priority to be u over a polynomial. And here's why. It's pretty simple to see. If u is ln of x, then du will be 1 over x dx. And notice, since dv would then be a polynomial that's multiplied to ln of x, in this case x to the third, its antiderivative, of course, is also a polynomial. In this case, the antiderivative of x to the third is 4x to the fourth. And why this is important is because since the derivative of ln of x is 1 over x, that will divide this polynomial just by x, and we'll get powers of x only, and that'll be easier to find the antiderivative of just using the power rule, antiderivative power rule. Also, if dv was ln of x, we would have to know the antiderivative of ln of x each time, and that's a pain to do. In fact, we did here for that reason. Okay, so I hope that kind of explains why we needed by parts here. When you have ln of x with not very much else, by parts is kind of the only way to handle things. There are some exceptions, like ln of x over x is a nice substitution problem, but ln of x by itself, for whatever reason, needs by parts. So now here, continuing with the formula, we have uv minus the integral of v to u. And just to kind of speed up the process a little bit, we're going to get 1/4 x to the fourth ln of x minus the integral of, so the 1/4 I'll pull out, and integral of x to the fourth times 1 over x. Notice that x to the fourth over x reduces the power to x to the third. And of course we have limits, but again, I'll consider those at the very end, so save the limits for later with integration by parts problems. And now the antiderivative of x to the third, of course, is, just like we saw here, 1/4 x to the fourth. 1/4 times a 1/4 that's already there is 1 over 16. X to the 4. And we're done with the integration, so we can write plus c. But again, we don't write plus c because this is a definite integral. So we're going to need to evaluate our limits now, like that, 2 and 1. Now, I think I have a little bit of space here below to write this, but just kind of bear with me. So when you plug in 2, you'll get 2 to the fourth, which is 16. 16 over 4 is just 4, times ln of 2. That's for the first term. Here, when you plug in 4, when you plug in 2, you get 2 to the fourth, which is 16 over 16 is 1, so that's minus 1. So that's for the first evaluation, plugging in 2. Great. Minus, when you plug in 1, you get 1/4 1 to the fourth, which is just 1/4, times ln of 1, but ln of 1 is 0, so we get 0 minus, when you plug in 1 here, this is going to be 1 over 16 times 1, so it's just 1 over 16. But notice this is just negative 1 over 16, and with the double negative you get positive 1 over 16. So in total, I'm going to actually just kind of erase as we go along a little bit, just because of space. And in total we have double negative, which is positive 1 over 16, and these two actually combine. Negative 1 is negative 16 over 16, so they combine to negative 16 plus 1 over 16, which is negative 15 over 16. And I'm going to actually leave it like that. And again, there are some pretty interesting ways you can simplify this, kind of like what we did here a little bit. You can bring the 4 in as a power to get ln of 16. You can then find a common denominator to write it as one fraction. You can do that before without bringing the 4 in as a power. I'm just going to leave it like this and call it a day. All right, so now this one's actually a little weird. there are a few things going on here. Notice we have t squared, but according to this, the powers don't really make a difference, but they kind of do when it comes to a power multiplied by a non-ln or a non-inverse function for that matter. So here, let's just kind of follow our noses a little bit. So much like we saw before, we're going to let u equal t squared because it's multiplied to an exponential, and then dv will have to be e to the 2t dt. Okay. du is going to be 2t dt, and the antiderivative of e to the 2t kind of requires its own u substitution, but it's pretty easy to handle. And there's a really nice way I can explain that everyone's going to believe me right away. So it's going to be itself, because antiderivative of e is itself, e to the x is itself. But then, because it's of 2t, which is a linear function, in other words, its derivative is a constant, by chain rule, if you take the derivative of this, a 2 comes out in addition to taking this derivative. So the derivative of e to the 2t is 2e to the 2t. But notice here that we just have e to the 2t without the 2. So, as a consequence of chain rule, and basically because of u substitution, we gain a 1/2. So anytime you have e to a linear function, its antiderivative is itself divided by the derivative of the power. Basically just the number in front of x, or in this case t. Alright, so again, that's not too difficult to verify that. And if you want, you can do substitution, but this is fine. Now we can use by parts. Alright, so it's a little depressing, but it's not too bad. You'll see what I mean. So uv, of course, is going to amount to, let's see, I guess it's 1/2 t squared e to the 2t minus the integral of, 1/2 and 2 actually cancel, which is nice. So this is just t e to the 2t, but this integral is actually simpler because instead of t squared in front, like I mentioned, seems a little weird, now we just have t in front. So we can actually use by parts again. And that's the part that's a little disturbing. You may have to use by parts multiple times in this kind of chain of events. So let's just do by parts here. So we're going to let u, of course, equal to t, and that's this part of the product. dv will be everything else, which is e to the 2t dt. So that again, v is equal to 1/2 e to the 2t. I hope I'm not writing too small. It's kind of small. And then derivative of u, in this case, is just dt. Okay. So now applying by parts again here, we have uv minus the integral of v du, and that integral will actually be pretty simple to do. Notice it's just going to be 1/2 e to the 2t, which you can pull out the 1/2 and then apply the rule for that. But this is still here. So we have 1/2 t squared e to the 2t minus, this integral is by parts, so let's write parentheses just to be safe, so that we know this distributes. So we get uv, so it's 1/2 t e to the 2t minus the integral of v du. Again, if you want, we can pull the 1/2 out of the integral, and then we get left over inside e to the 2t dt. Perfect. And there are no limits here. This is an indefinite integral, so we'll write plus c at the very end. And we are almost done. We're actually basically done. All we need to do now is distribute the negative and then find the antiderivative of this and write plus c. That's it. So let me rewrite this. So we have 1/2 t squared e to the 2t. The negative distributes, so this becomes negative 1/2 t e to the 2t plus, I will write 1/2, but what's the antiderivative of e to the 2t? It's 1/2 e to the 2t. So notice we gain another 1/2 here in multiplication, so that combines to actually 1/4 e to the 2t. And now we can write plus c because we're integral free. And let me attempt to box this without getting in the way too much. That looks okay, I guess. And notice nothing combines, even though it looks like they all have a lot of stuff in common. They're not like terms. Notice the powers of t multiplied are all different. In fact, you could write this a little factored, which would look kind of nice. It would be a polynomial, essentially, times e to the 2t. But I'm going to leave it like this. Now what I want to show you is a lovely shortcut to the scenario where integration by parts repeats. Right, so now moving on, I have these three examples, and looking at them with integration by parts in mind, you may think, what are you doing? Because we have, this is the same one we actually just did, but here the power is x to the fourth. Based on this example, well, the way we did it, by parts had an appearance twice. Here, if you kind of run through the same argument, it'll actually have an appearance 4 times. So we have to do integration by parts here 4 times and here 3 times, and you may think you're crazy. But I'm not. Well, maybe I am. But it's actually not that bad with the shortcut in mind, and the shortcut is known as the tabular method. At least from what I'm told. And the tabular method is pretty cool, but it only applies kind of sometimes. It really only applies when you have a polynomial multiplied to a function that you can take the antiderivative of essentially indefinitely. And exponentials and trig functions are examples of those. We can take the antiderivative of e to anything all day long, so long as it's of a linear function, similar to a trig function. Something like ln of x, it's hard to take its antiderivative, and its antiderivative is even harder to take the antiderivative of. So let me explain what the tabular method looks like. So we're going to create this table that is essentially 2 columns, and how many rows depends on where you start. So some people call these columns different things. I'm going to call it D and AD, not for dad, but D for derivative and AD for antiderivative. And we're going to start with, well, this is basically a application of by parts. So we're still going to go with the same scheme as far as what's u and what's dv. U will take the derivative of, dv will antiderive. But only here we're kind of seeing them both go down instead of opposite like we saw with IPP. All right, so u, of course, will be t squared, much like in the previous example. Again, same example, just different method. E to the 2t we're going to take the antiderivative of, and here's how tabular method works. We're going to take the derivative of this column of t squared until we get to 0. So its derivative, notice, is 2t, then 2, and then derivative of 2 is 0. Then we're going to take the antiderivative until we catch up to that 0. Antiderivative of e to the 2t was itself, but notice each time we divide by 2. So this is divide by 2, and then again you divide by another 2, and 1/2 times 1/2 is 1/4 now. Great. And now what we're basically going to do is multiply diagonally, but because of the integration by parts formula having a minus, what this basically amounts to is that every time we would apply by parts, you get another minus. Remember when you distributed the negative and that new negative became a positive? Well, this happens. We get an alternation of signs starting with positive, and these get multiplied diagonally like that. I need to do one more actually to catch to that 0. I was missing one, wasn't I? So this is going to be 1/8 e to the 2t, my mistake. So good. Because again, why 1/8? Because we divide by 2 each time because of the 2. Perfect. And now, if we multiply these and combine, we'll get our answer, and it should be the same exact answer we got before, but with much less effort. Okay. So the first term here is going to be positive 1/2 t squared e to the 2t. This is going to be negative 2/4, which is 1/2, t e to the 2t. This is going to be positive 2/8, which is 1/4, e to the 2t, and then we're done, so write plus e. And this is exactly the same as the result we got before, and it should be. So we can verify this method works. So now I'm going to do this one using tabular method as well. It's going to be a little longer, but there are limits, so hopefully that kind of cleans things up. Let's see. So we're going to start with D and AD. Our D will be something that you want to take the derivative of until it's 0, so a polynomial, and 27 x to the 4th is okay for that. In fact, maybe it'd be better to partner off 27 with cosine because you divide by 3 each time. Otherwise, we'll have to multiply and then the number gets kind of large. Yeah, so if you don't mind, I'm going to do that. So I'm going to treat this as u and then this as dv. So this is u and this is dv. In other words, we take the antiderivative of 27 cosine of 3x until we get to the 0. So x to the fourth, its derivative is 4x cubed. Then 12x squared, hope I'm not writing too small. Then 24x, then 24, and then 0 finally. Great. Now to catch up to the 0, we're going to take the antiderivative of 27 cosine of 3x. Now we actually haven't really done what I'm about to do yet, but it's similar to this idea. When you have e to a linear expression, you can take its antiderivative like normal, but you have to divide by the number in front. And I even mentioned this actually works for trig functions as well. So the antiderivative of cosine is sine, but since it's of 3x, we have to divide by 3. So just divide 27 by 3, you get 9. And you can always check this by taking this derivative and notice you'll get the exact same thing above. Antiderivative of sine is negative cosine. And again, since it's a 3x, we have to divide by 3. 9 divided by 3 is 3. So you see why I wanted to partner off the 27 with cosine. Okay. Antiderivative of cosine is positive sign, so the sign stays negative. It's of 3x, so you divide by 3, and 3 divided by 3 is 1. And antiderivative of sine is negative cosine, so we finally get the double negative, so that cancels out. It's positive. But since it's of 3x, we have to divide by an additional 3. Okay. And finally, antiderivative of cosine is sine. Since it's of 3x, we have to divide by an additional 3. So we get 1 over 9. Fantastic. Now, we can multiply diagonally like this, kind of a lot. Alternate the signs. Plus, minus, plus, minus, plus. And we're good to go. Then we have to consider the evaluation at the end. Probably should have wrote this a little more over there because it's going to be a little long. But I think we'll be okay. Maybe not. This is probably a little too ambitious. But let's see. We're going to get positive 9x to the fourth. So I'll try to write this the best I can. 9x to the fourth, sine of 3x. Plus, because it's double negative, 12x to the third, cosine of 3x. And then negative 12x squared, sine of 3x. And then minus 24 over 3 is 8, so that's minus 8x, cosine of 3x. And then finally we're here, so we have plus 24 over 9, which reduces to 8 over 3, by the way, sine of 3x. And I would write plus c, but this is definite. So instead we're going to evaluate this between the limits, 0 and pi over 3. Now the really good news here is that when you plug in 0, everything becomes 0. I think everything becomes 0. Yeah, because notice all of these terms are multiplied to an x, and when you plug in 0, those terms all go to 0. The last term isn't multiplied by x, but sine of 0 is 0. So this we don't actually have to worry about, so I'll put a slash to that. When you plug in pi over 3, well, the signs will actually go to 0 in that case, because sine of 3 times pi over 3 is sine of pi, and sine of pi's go to 0. So maybe I can write that out real quick. I don't know if I can write it here in this space below, but I'll write it over here and just erase it after. So when we plug in pi over 3 here, we're going to get 9 pi over 3 to the fourth, but then we have this times sine of pi, so that's 0, plus 12 times pi over 3 to the third, times cosine of pi, because again, 3x is equal to pi when x is equal to pi over 3. And then we have negative x squared. So it's 12x squared, sorry. Pi over 3 squared times sine of pi. And again, this guy is 0. Oh, by the way, cosine of pi is negative 1. So that'll change its sign actually. And then we have this negative 8 times, so I don't have space there, so I'm right, minus 8 times pi over 3. I probably should have started over here, but that's okay. Times cosine of pi, good. And then finally, plus 8 over 3 times cosine of pi, times sine of pi. Plus 8 over 3 times sine of pi, times sine of pi. And again, cosine of pi is negative 1, but sine of pi is 0. So every other term here actually goes to 0. So I'm just writing this to the side for kind of scratch work. So those cancel, those cancel, those cancel. So really we're just left with these things. And if you want to kind of expand things out just a little bit, we can do that certainly. Notice this becomes negative, that positive because of double negative. So in fact, for this one, I'll write that, and I'll actually write the answer here because it's just two terms. So here I'll write the positive term first, even though it's in the opposite order to begin with. I get 8 over 3 pi, and that's it. So it's 8, let's just write it as 8 pi over 3. Okay, good. This guy is going to be, let's see, it's going to be 12 times pi cubed over 3 cubed. So let me just write that, 12 times pi cubed over 3 cubed, which is 27, by the way, and it's negative. Now you can divide by 3 to get 4 on top and 9 at the bottom. So this is minus 4 pi cubed over 9. So this is our answer actually. We're done. Kind of crazy because it looked like a little much, but then evaluating actually turned out really nice. If you want to write this, of course, is as one fraction, multiply this top and bottom by 3, then we'll get 24 pi. Let me just rewrite that a little bit. Okay, so 24 pi minus 4 pi cubed all over 9. And these are just as acceptable as the other one. Well, they're both just as acceptable. Now I'm going to erase this and continue on with this example. But this example is kind of going to be very similar. You'll see. All right, so here we're going to, of course, use tabular method again. So we have D and AD columns. For D, we're going to start off with a polynomial whose derivative is eventually 0. So it's x to the third. Derivative is 3x squared. Derivative is 6x. Derivative is 6. The derivative of that is 0. And e to the negative x, its antiderivative will be itself times negative 1 because you have to divide by the number in front of x, which is negative 1. So this is e to the negative x, negative e to the negative x, double negative, so positive e to the negative x. This will be negative e to the negative x again, and then positive e to the negative x. So notice what happens in this case, we just get alternate signs here. And what's kind of funny is that we have alternate signs from the tabular method. So we kind of undo that, maybe? Let's see. So this will be positive, this will be negative, this will be positive, this will be negative. Yeah. So we kind of see in total, if you look at it, negative, 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 they're all negative. And they're all multiplied to e to the x. So if you want to expand that out, I guess we can. Or factor it out, you can. But I'll just write it as is, just so we're kind of used to this scheme here. So we have negative x cubed e to the negative x, minus 3x squared e to the negative x, minus 6x e to the negative x, and then finally minus 6 e to the negative x. And again, don't write plus c because we have limits. And when we plug in 0, it's not just 0. These are all 0. The first three terms are because they contain an x in their product. But this last one is going to be negative 6 e to the 0. E to the 0 is 1. So when plugging in 0 to the last term, we're just going to get minus negative 6 e to the 0, which is just negative 6. So that's the last term considered. Plug in the 1 to the first term. Well, they're all multiplied by e to the negative x, so that's going to be e to the negative 1. And the x's kind of go away because powers of 1 are just 1. So here we get negative e to the negative 1, minus 3 e to the negative 1, minus 6 e to the negative 1, minus another 6 e to the negative 1. So I hope we can kind of see that. And notice again, they're all multiplied by e to the negative 1, which is really just over e. So if we combine them, again, they're all negative. We get 1, so just looking at the coefficients. I have 1, 3, 6, and 6. They're all negative. So 1 plus 3 is 4, plus 6 is 10, plus 6 is 16. So they actually all combine to negative 16 e to the negative 1, or negative 16 over e. And then we have plus this 6. And again, if you want to combine these into one fraction, you certainly can. But I'm not going to. I'm going to leave it like that. And now we're going to see one last thing, one last example, and I'm going to try to summarize what we learned in 7.1 finally. Right, so finally, this is going to finish us off along with a nice summarization of integration by parts, by guidelines, how to assign u for a given integration by parts problem. Now, this problem here is a pretty infamous problem, honestly. The book actually does an example of e to the x sine of x, but I'm going to generalize it for sine of x. If you want to do e to the ax times cosine of bx, you can follow along with this example here, and you'll see that it's going to be very similar actually. So I'm generalizing what the book has, where you have actually a number multiplied to x in each of these, and they're different numbers, let's say. This is indefinite integral, of course. Now, we'll see why this problem is so kind of, I guess, I said infamous, but why it's so interesting is, well, by parts is essentially going to be applied kind of infinitely many times. So we're essentially going to be applying by parts until we see a pattern, until we see something kind of familiar. So let's just cut to the chase. Now, as far as what's u and what dv is, we actually haven't seen a case before where we have two things multiplied where one's exponential and one is trig. As it turns out, it doesn't really matter which one you do. The guidelines we'll see will say otherwise of what I'm about to say, but to be quite honest, in this case, either works. So I'm going to actually let u equal e to the ax. Okay, so that means dv would have to be sine of bx dx. So that means v is the antiderivative of sine, which is negative cosine. But since it's of bx, we have to divide by b, so 1 over b cosine of bx. Derivative of e to the ax is a e to the ax by chain rule. Of course, we get a dx attached. That's du. And now applying the formula for integration by parts, we get uv minus the integral of v du. And I'll actually, if it's okay with you, I'll write the result over here just for space. Let me box this so it doesn't get too much in our way. So we get uv that's going to amount to negative 1 over b e to the ax cosine of bx, like that, minus the integral of this times this. And notice first off it's a double negative because of this, so if we pull that out we get positive instead of negative. And the constants are a and 1 over b, that's a over b, so pull that out of the integral. And now we're left with the integral of e to the ax and cosine. Look at that. So now we actually went from e to the ax times sine of bx to e to the ax times cosine of bx. So now we're going to apply by parts again in the same way. So u is still going to be e to the ax, then dv would be cosine of bx dx. And I'll write that actual table over here, just so we can compare. So u is going to be again e to the ax, so that means du will of course be a e to the ax dx. dv then will be cosine of bx dx. So the v is the antiderivative of cosine, which is positive sine, divided by b because it's of bx. Perfect. You lose the dx when you take the antiderivative. And again, using by parts, I really like to draw these lines like this. It looks nice. Because it helps you remember the formula, really. In fact, notice I haven't really rewritten the formula since the very beginning. This pattern is really the formula to some extent. So now I'm going to write our result over here, if that's all right. And it's going to be equal to, so remember, it's this integral. So just to write everything, we have negative 1 over b e to the ax cosine of bx plus a over b times that integral, but that integral is replaced by the by parts expression, which is uv, that's going to be 1 over b e to the ax, okay, sine of bx, good, minus the integral of what? Minus the integral of, well, notice the constants here are a and 1 over b, so we can combine those as a over b and even pull it out of the integral because, of course, it's constant. And we get e to the ax sine of bx dx. Great. And notice that we can distribute this this a over b, and so I guess I'll just do that here. So we get negative 1 over b e to the ax cosine of bx cosine, sorry about that, of bx plus, this is going to be a over b squared e to the ax sine of bx. We're in a little bit out of space, but it's okay. A over b times that's going to be a squared over b squared. Integral of e to the ax times sine of bx dx. And what you may notice is that we get from sine to cosine, so just kind of to summarize what this is doing here, one step of integration by parts gives us the integral of e times sine to a times cosine, and then another round of by parts gets us back to an integral involving sine multiplied by e to the ax. And this is good because, and of course we could continue doing this, like I said, in like kind of this infinite way, but we're kind of stuck in a loop. Because what we started with, and in fact normally what's done is you call the original integral I in the event that this repeat happens. Notice that this is just a repeat of I. So this whole thing is equal to I. So if you replace this integral with I, so allow me to do that here, we actually have an equation for I. Of course, I for integral. So we can actually solve for I, and I want to do that, but I don't want to spend too much space, and I'm kind of taking a lot of space up as is. So maybe I'll just write the result. So I'll write I equals, and I'll tell you what the result is, but maybe I'll use some algebra here. So if you add this to this side, notice that both times I, this is 1 times I, that's a squared plus b, a squared over b squared times I. So if you add this to this side, you get 1 plus a squared over b squared all times I. And notice if you combine these with a common denominator, 1 is of course b squared over b squared, so this is a squared plus b squared over b squared. So to solve for I, we'll divide by that. So it's going to be this whole thing essentially multiplied by the reciprocal of this. And again, this is a squared plus b squared over b squared is equal to the thing in brackets I wrote up here. So then dividing by this, which is just times its reciprocal, we'll get our answer. So the integral is actually equal to this. It's indefinite, so I'll write plus c, of course, at the very end, which you were probably waiting for. So I have a squared plus b squared. No, I'm sorry, the reciprocal is the other way around. That's really b squared over a squared plus b squared all times this. Now notice that if you distribute the b squared in, it's kind of interesting. Let me kind of see how we can write that. Yeah, if you distribute the b squared in, it cancels with these. So let me write 1. And let's say if we distribute the b squared in, it cancels this. B squared over b is just b. So it's going to be negative. Maybe I should write that one first or second because it's negative. So I'll write this one first after distributing b squared. I hope it's not getting too complicated. So we have a e to the ax sine of bx minus, so distributing b squared into this one, b squared over b is just b, so it's minus b e to the ax times cosine of bx, close brackets, and then we can write plus c, and that is the answer to this indefinite integral. Crazy, 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 crazy. Apply integration by parts till you get the same integral you started with. There are actually a ton of different examples that have this property going on, but this I think is probably the most basic or most classic example. All right, so now that that's done, I'm going to erase this work here, and I want to not generalize, but I want to give you guidelines for assigning U to integration by parts. And it's actually a really nice acronym that you can all remember if you like. Some people will change it up a little bit, but the common one, at least the one I know, that most people know and learn, is LIATE. L-I-A-T-E, which of course these all stand for different things. They basically stand for types of functions. So L stands for logarithmic, A stands for algebraic, I skipped I, sorry. I stands for inverse. Really it's inverse trig, but I'll talk a little more about that in a second. A stands for algebraic. There we go. T stands for trigonometric. And E, of course, stands for exponential. So, of course, I can give examples of these. Log basically will be seen ln of x. You can also see like log base 2 of x, which we haven't seen. They're less common, but if you see that, then that would be U opposed to anything else. Inverse trig examples include, let's say, I don't know, sine inverse, cosine inverse, tangent inverse. You get the idea. In fact, in general, any inverse function has priority over any of these. So basically, there are inverse functions, there are non-inverse functions, so to speak, and then we have, we have algebraic in the middle. In fact, if you take a look here, inverse trig and trig are inverses of each other, logarithmic and exponential are inverses of each other. So that's kind of like the hierarchy of what it has priority to be u. Now algebraic, you think of powers of x, like x squared, even polynomials like x cubed minus 2x. But it goes beyond that. You can include radicals, let's say like radical x minus 1, or even like 1 over x, something like that, or even combining those. Trigonometric, of course, are sine, cosine, maybe even cosine squared. That's a little iffy, but I guess it kind of works. Exponential would be, of course, e to the x, e to the 3x. Even actually 2 to the x is considered an exponential function. But notice e to the x, similar to ln of x, are the natural of those. So ln of x is the natural logarithm, or e to the x is the natural exponential. Okay, that concludes our discussion on 7.1. It was kind of long, but honestly, you'll see a lot of chapter 7 stuff, or a lot of chapter 7 lectures anyways. Will be pretty thorough. I try to show as many examples as I can. I try to go over all of the cases you'll be seeing in homework problems. And I'll see you in the next videos for the rest of chapter 7. Hope you enjoyed. I'll see you then.